average temperature of the air inside the balloon, and we have the mass of the unfilled balloon and the payload. Okay, well, at least the first step, we know that
most of them are about 2,800 cubic meters.
the buoyancy force has to at least balance the weight. So
and the volume for
F
most hot
buoyancy, yeah.
Most hot air balloons, it says, are about 2,800 cubic meters. So we say 3,000 cubic meters.
Right. So the buoyancy force has to be at least equal to the weight or greater than the weight. Let's just say equal. So that means what's F buoyancy? That's the density of the surrounding air. Let's just call it rho 1 times the volume times the gravity, right? And that has to equal the mass m plus the mass of the air times gravity. So that's what we need first, yeah. Rho 1 Vg, and V here is the volume of the balloon, because it will displace volume of balloon, because it will displace air equivalent to its weight, because we know that mass equal density times volume. Okay, and so if I multiply the volume of the balloon, which will be the volume of the air displaced by the balloon outside, times the density of the balloon, which is, we called it rho 1, so this is rho of the balloon, rho of the air, surrounding air, density of surrounding air, because that's where this is taking place, times gravity. That should equal to the gravitational force. So this is the first thing we need, yeah. Okay, now we need to relate this to temperature. Okay, so small m, that's small m is the this is the mass of the air inside the balloon. We know that the mass of air inside the balloon is equal to the rho on the inside. I'm gonna call it rho I, just to distinguish it from the outside of the balloon. Actually, I'm gonna call this rho O, meaning outside the balloon, and this is rho I, inside the balloon. So rho I times the volume of the balloon will give me the mass of the air inside the balloon. So I'm gonna take this and plug it here, right? So we call this, just to be clear, surrounding air. Okay, so then we're gonna get rho 0 Vg is equal to m plus, we could cross out the g's, so this is gonna be rho I times V. Okay, so this is the first, and then we could move this here, so we get V into rho minus I, or yeah, we could divide by V, so we get rho outside minus rho inside is equal to m over V. Okay, so this is one equation. Well, we know
there's no motion involved.
we have to use the ideal gas law to relate the densities to the temperature, to the moles.
It's a linear relation.
So yeah, let me see how this is gonna fit. So PV is nRT, right?
Yeah.
for air, well, I could play with this equation. The number of moles is just the mass over the molar mass. The molar mass, let's just call it mm, and RT. If I divide both sides by V, I would get P times the molar mass equal density equal mass. Yeah, mass over volume, RT, and this is nothing but the density. So now I have the pressure times the molar mass equal the density times RT. Okay, great. So we already know the molar mass for air, so that means the density of the air outside will just be the pressure times the molar mass divided by RT. Okay, sounds good. And let me look up what the so the molar mass for a mole of air. So here, this is the rho for the air outside, and with the same exact token for the inside will be the pressure, which will be the same, because you have to have the same pressure right at the edge, equilibrium. So times the molar mass over, so this here would be for T outside, if this is the density of the air outside, and this here would be inside for the temperature inside, since this is the density inside. Okay, and then we're gonna take these two and plug them into equation, let's call this equation 2. So plug in 2. Okay, great, and we're gonna get P. Since these two are the same with the R, I'm gonna factor them out. So we're gonna get P times the molar mass of air divided by R times 1 over T outside minus 1 over T inside, right? That has to equal M over V. Okay, good. Yeah, I got an equation, and the only unknown in this equation is T inside, because I can estimate everything else. Pressure. Yeah, I looked it up. The diameter was 15, which is 15, 16. Let's just say that the radius is about 8 meters. On a sphere approximation, this would be 4/3. Okay, so if you want to go,
it's 3,000 cubic meters.
if you're gonna go a little bit less than a sphere, well, it's a little bit more. That's why I kind of added a bit to the radius.
It actually lists the volume at 3,000 cubic meters.
You see?
Well, that's what it says. Most of them have a 2,800 cubic meter volume, the most common one. So I just rounded up to 3,000.
Yeah, so let's see. Okay, so then we'll blow up the radius a little bit. Pi r cubed. So this is 4/3 pi 8 cubed. Let's see. 2,145.
Well, it said the most common was 2,800.
2,800?
Yeah.
I mean, more than 8 meters on the radius?
Yeah, well, it's not a perfect sphere. It's like elongated.
so it should be less than this.
Well, or a little. Well, the radius, I guess, is the top part, but it's a little elongated, so it might be more. It's like they're pretty stretched out.
Okay, that's fine. It's an approximation.
So I just rounded up to 3,000.
Let me use this based on a sphere calculation. Let's see what we got. 2,145 meter cube. Okay, so this is the volume of the balloon, right? Temperature outside is what?
273.15.
Kelvin?
Yeah.
That would be 0 Celsius.
Well, I was doing STP.
No, why?
That's
Let's just take the average temperature of air. What would that be? Average.
Well, then you'd have to change that. Then the molar volume would go up a little bit. It would actually go up a considerable amount. Well, it depends where you are.
Let me see what we get usually. 20 degrees.
Yeah, that's taken as room temperature.
Right?
Yeah.
Yeah. So why
But
not
then
we do that?
But then the
So
molar
that's-
volume would go up about like 5 or 10% for the molar volume.
Molar volume does not come into my equation.
Yeah, that's true because it's just a ratio.
Yeah. So.
Oh no, but it would come into the equation because it's a finite volume inside the balloon.
So let's just say 290
But it
degrees.
would come into, yeah, but
Kelvin.
It would come into the equation because you would have a maximum. You'd have a maximum buoyancy if you. The maximum buoyancy would go down as the temperature increases because the density of the air outside is equal.
Okay, so we're gonna take the temperature to be 290, and then the pressure at that altitude is about 1.01 times 10 to the fifth.
I don't think the pressure is going to matter in this.
That's well, I need it in the equation.
Oh, if you're doing it that way.
Yeah, 10 to the 5, and then well, that's in pascals, and I still have the R is universal gas constant. That's 8.31. The units on that are joules per mole Kelvin. Okay, that's it, and then we're just gonna solve for the T outside from this red equation here. So let's see, 1 over T or T inside, let's just move everything else to the left. Oh yeah, one more thing, big M, the molar mass of air we said is that turned out to be, what was it, 28 something, yeah, 28.96 grams, 28.96, so that's 2.90 times 10 to the minus 2 kilograms. That's for air average. Okay, we have everything, and big M is given in the question. That's the mass without that's the mass of the unfilled balloon and the payload, so that's 500. Okay, now let's take this red equation here and work it out for T inside. So we get 1 over T outside minus 1 over T inside equal Rm divided by P molar mass V. Move move this to the right, and so 1 over t t inside will be 1 over t0 minus r m over p molar mass v, and then I could just reciprocate this, so ti will be all that to the minus 1. And so let's plug the numbers in. We get 1 over 290 minus r is 8.31 times 500 divided by 1.01 times 10 to the 5th. Molar mass is 2.90 times 10 to the minus 2, and the V is 2145 meter cube. Okay, and this whole thing is raised to the minus 1. And let me see what we get. So plug this onto the calculator. I got 358.8 for the temperature inside the balloon. 0.8 Kelvin. That sounds like a very reasonable temperature. Find the mass. Okay, the mass of the air inside the balloon. Once we know the temperature, that should become straightforward. So we know from the ideal gas law PV equals nRT, and we already manipulated this to get this is N is mass over the molar mass of air, RT. We divide by V, so we get P times the molar mass equal mass over volume is just the density, so inside, so this is rho I. Oh wait, but I'm interested in the mass. I don't want this to go away, so let's leave it. V equals mRT. Okay, and if we're talking about inside the balloon, the mass, so if this is the mass of air inside the balloon, this has to be inside the balloon. This is the volume of the balloon, and the pressure is the same, so we get mi to be p mmv over rti, and so that's 1.01 10 to the 5th. We said that this was 2.9 times 10 to the minus 2 molar mass of air. The volume of the balloon we estimated to be 2145. 2145, and we're going to divide this by 2145, and divide this by R, 8.31, and the temperature inside we just found 358.8 Kelvin. Okay, plugging this in. 2107
The simplest way to do this would be with N.
kilograms. The simplest way to write this, to do this, is to start with the buoyancy force balancing the gravitational force.
Yeah.
And then go from there. Basically what I did, if you want to know in summary, is I balanced the gravitational force with the buoyancy force. Buoyancy force has in it the density of the air outside and the volume of the balloon. Partial mass has in it the density of the air times the volume of the balloon. And from there on, I related between the density outside and the density inside. with the volume of the balloon, and then I use the ideal gas law to express the densities in terms of the other variables, pressure, the molar mass of the air, because we know that gas constant and the temperature, in the case of density outside, temperature outside, in case for density inside, temperature inside. And that's how I was able to get from the density to the temperature. So I substituted, I replaced densities with expressions having temperatures in them, and then I plugged them in. I know everything else, and I solved for the temperature inside, since everything else is known. Pressure, volume of the balloon we approximated, the molar mass of the gas, the universal gas constant, the temperature outside. All these variables we can approximate, or we have good numbers on. And we figured out the temperature inside. And once we know the temperature inside, it's just a matter of plugging that back into the ideal gas law to figure out the mass of the air inside, because now we have the temperature inside. So I just use the ideal gas law inside. I know the pressure has to be the same. And by the way, that's an argument I use on the first part too, because the pressure is the same inside and outside for equilibrium to happen. And so and that gave us the mass of the air inside the balloon.